Hi, everybody. I'm going to talk about some formal charge examples here. So for this first example, we want to be careful about this little assumption that I have put in here. We're going to assume that for this example, all the carbons are neutral, meaning that all the invisible hydrogens that we imply are present. Just because when you're starting off, it's really easy to look at something that doesn't have the hydrogens drawn in and think that, you've got a carbocation or something going on. But most of the time it's not that. Just to be very clear, any kind of formal charge questions that I ask, I will give you that information as to whether or not, what's going on with the carbons, what's going on with those implied hydrogens. And we're going to see a little example of that later on. But for this example, we're going to kind of consider all of the carbons have their full octet. They're all neutral. They have all of their implied hydrogens present. So for this, notice I don't have any lone pairs on any of my oxygens or nitrogen atoms. So we need to kind of keep an eye on that. So the first thing we need to do is really to draw in those lone pairs. Oh, forgot something that I set up for myself here. Okay, so we're going to draw in those lone pairs and we're going to add the lone pairs on oxygen or nitrogen to get up to 8 electrons. So basically you want to count how many electrons it has right now. And that missing number to get to 8 is going to be the lone pairs that you're going to add. So if we look at this nitrogen first, the nitrogen has 2, 4, 6, 8 electrons from the bonds that it already has. So that means we're already at 8. There's no lone pairs to be added because we're already at that perfect octet number. If we look at this oxygen, so we've got 2, 4, 6. So that has 6 electrons around it currently. To get up to 8, we would need 2 more, which is going to give us 1 lone pair. For this oxygen down here, we've got 2, 4 electrons in bonds, which means we're going to need 2 lone pairs to get it to 8 with that full octet. Okay, so now that we have our lone pairs, we can go ahead and get to assigning our formal charge. Remember, this is going to be valence minus owned. Okay, owned is going to be the number of bonds and all the lone pairs added up. So let's go ahead and start with our nitrogen. So for nitrogen, our valence is going to be 5. So anything that we're doing with nitrogen is going to start with that valence of 5 electrons. So if we're counting up the bonds, we've got 1, 2, 3, 4 electrons that are owned in bonds. So 5 minus 4 is +1. That nitrogen is going to get a positive charge. If we go ahead and look at this oxygen here. Okay, so our valence for our oxygen is 6. For the owned, we've got 1, 2, 3, 4, 5. Okay, so we got 3 bonds, 1 lone pair, so a total of 5. So 6 minus 5 is +1. So that's going to get another positive charge. We go down and look at this oxygen at the bottom here. Again, the valence is going to be 6. For the owned, we've got, change this. There we go. 1, 2, 3, 4, 5, 6. So 2 bonds, 4 lone pair electrons. So that's going to have a charge of 0. So that oxygen is neutral. We don't have to put any charge on that one. So let's go ahead and look at the second example. So this is an example of one where I have drawn in hydrogens here. So I have taken away all the guesswork of figuring out where the hydrogens are implied or not. And the reason for that is when you're doing charges on carbon, it gets a little bit weird in there if you don't have the hydrogens drawn out, especially if you're kind of new to it. So for this one, we've got carbons. So any carbon that has 4 bonds onto it is neutral, right? So if we're looking at this carbon, for instance, let me try to get that better. So our valence is going to be 4. Our owned is 1, 2, 3, 4. And that's going to be 0. So that's going to be the same for this one, where we've got 1, 2, 3, 4 bonds. This one has 1, 2, 3, 4 bonds. This one, 1, 2, 3, 4 bonds. Okay, so I'm not going to write all of them down, but I'm just going to go ahead and do this one at the end too. Okay, so those are all neutral. The one that we kind of want to keep an eye out for is one of those carbons has a lone pair on it, which is not a normal thing. It's definitely a little bit of an unusual situation here. So if we go look at this, the valence is still going to be 4. But now our counting for our own is going to be a little bit different. So we've got 1 for that bond, 2, 3. So we've got 3 from bonds. And then we go in and count 4 and 5 for the lone pair. So 4 minus 5 is -1. So that carbon gets a minus. That is a carbanion, okay? All right, so then let's look at this example. Oh, again, we have a situation where all of the hydrogens are drawn in. So if we're looking, this one has 4 bonds, this one has 4 bonds, 4, 4, 3, that's something suspicious, 4, 4, okay? We again have an oxygen that only has 2 bonds, so we've got 2, 4, so we need to add 6 and 8, so we have our lone pairs there. So we can start with the oxygen here. Valence is going to be 6, owned is going to be 1, 2, 3, 4, 5, 6. That's 0. Then if I look at this carbon over here, valence is still 4. My owned, we've got 1, 2, 3 bonds. That's it. So 4 minus 3 is +1. So that is going to be a carbocation. Okay. So definitely things to keep in mind, patterns to kind of absorb a little bit. Just remember to keep practicing and let me know if you have any questions.